Yes, sir, you can start.
Okay. So is my screen visible to everyone?
Yeah, it is visible.
Okay. So welcome to this webinar on the course Well Testing, Design and Analysis. So to tell about me, my name is Vinod Kumar. I am from India. So I have completed both bachelor's and master's in petroleum engineering recently, and currently I'm working as a reservoir engineer in India. So this course is a very important course for any reservoir engineer as well as production engineer, because reservoir and production talk to each other on a daily basis. So what conclusions a reservoir engineer makes will be the input for a production engineer to monitor and optimize production. So to people who are new to this well testing, design and analysis, I want to just brief you about reservoir engineering and why we call or why we map this well testing in reservoir engineering. So if you look at your left hand side, there are some definitions for reservoir engineering from renowned scientists and researchers. So the primary functions of reservoir engineering is the estimation of hydrocarbon in place, calculation of recovery factor, and the attachment of time scale to recovery. That is given by LPDEC. Similarly, reservoir engineering deals with the occurrence and movement of fluids in reservoirs and their recovery. That is given by N. Clark. The job of a reservoir engineer is to produce oil and gas reservoirs in such a way that the recovery is maximized. That is given by H.C. Slider. The responsibility of reservoir engineering is to make and interpret indirect measurements of the quantitative characteristics of reservoir. So this is something important to us as far as this lecture is concerned. So we try to make and interpret indirect measurements of the quantitative characteristics of the reservoir and to forecast the behavior of reservoir under any potentially useful production scheme given by HRAMA. Also by LPDEC, the key objective of reservoir engineering is to turn the time mirror around, ensuring a coherent image of future production of an oil field. That is a part of simulation and modeling, where we do history matching and we predict the future behavior of a reservoir. So if you look at the tree chart given here, reservoir engineering has two broad spectrums. One is field operations and the second is classical RE. So in field operations, we do well testing, that we go to field and we take data from our well. I'll explain in the upcoming slides. We also do reservoir monitoring. We do production forecasting with the production engineers, and we also involve in field development. So reservoir engineering has these four wings under its field operation spectrum. Also in classical RE, we have material balance, decline curve analysis, PTA, which is also called as pressure transient analysis, that is also interused as well test analysis. And also we have RTA, also called as rate transient analysis. So this PTA and RTA are the main two uh, regions where we map them onto a common head called well testing. So these both, well testing and PTA, are something which are the objectives of this webinar. So coming to the course objective, this course stresses practical application of well test theory to design and interpret pressure transient tests. An approach to well test interpretation is emphasized throughout the course. This course also will focus on different types of tests and techniques, both analytical and graphical, also called as numerical, for data representation and analysis of well tests. The audience would be engineers and geoscientists, and of course students who want to understand the well testing principles and interpretation techniques to design, analyze, report, evaluate results, or intelligently participate in the well testing process. So experience in production and reservoir engineering is recommended, but knowledge is mainly recommended. Experience in testing is required, is helpful but not required. So this will be a fundamental and a progressive course from fundamental to advanced, which will let you know what is exactly happening in the current scenario of well testing, design and analysis. So outcome would be the students will be able to analyze, draw down and build up tests in oil and gas wells, identify flow regimes using the log-log diagnostic plot, describe the characteristic pressure behavior for common bounded reservoir geometries, where we understand from log plot that the reservoir has hit the boundary. The types of techniques covered will include diagnostic plots for derivative, for drawdown and build-up tests. Also, the participants will learn about the interpretation of complex data such as those from well tests in naturally fractured reservoirs, hydraulically fractured reservoirs, horizontal wells, along with gas and gas condensate reservoirs. There will also be a pre and post assessment at the end of the course, where we try to track what knowledge you have got before the course and also after the course. So to start with, we want to see what is the objective of PTA, also called as pressure transient analysis. As I have told you, we will be using these both terms, well test analysis and PTA, interchangeably. So if you look at this picture, we have a reservoir, the bulk reservoir, where we have drilled a vertical well, and maybe it has been completed with a casing as well as cementing. Just for representation purpose, it is given open hole here. So we have a tubing installed, and if you can see, we have a pressure recorder that is also called as gauge. So in field operations, we generally use EMG, called as electrical memory gauge or electronic memory gauge, sorry. So this EMG has a potential to record pressure and store within itself. So it will try to store that data of pressure versus time, and this data will be the reference or the input for well test analysis or interpretation. So the objectives of PTA would be to evaluate reservoir pressure, evaluate reservoir fluid samples that are collected, evaluate reservoir properties like K, S, etc., the permeability and skin factor, which are most important parameters to evaluate the field life as well as the well life. Also to estimate reservoir volumetrics, the fluid in place and drainage area, because from this well test analysis, we can understand what is our drainage area, like up to what point in a particular pool or in a particular field our well is getting fluid from. So we can re-estimate our reserves. That is also called as the fluid in place that we can calculate from this well test analysis or the PTA. So input data required for PTA would be the bottom of pressure data, as we have already discussed. The pressure recorder records the data, and that is the input, primary input, accurate to less than 1 part in 10,000 or more. This 10,000 or more is the time limit. Also, we require surface flow rate data, because this flow rate data is important to evaluate drawdown test, because when we look at build-up test, we need to flow the well for some period of time, that is usually 8 hours in industry practice, because we want the pressure to stabilize and then we suddenly shut in the well. So we need surface flow rate data that has a characteristic bottom hole flowing pressure and the corresponding PI, the productivity index, the fluid properties, which will be a primary input for well test design and analysis, that is the formation volume factor, viscosity and compressibility, and the reservoir parameters like the net pay, H, reservoir extent, RE, the reservoir radius, RW, the wellbore radius, and fluid compressibility, that is already discussed. So the results of PTA would include the capacity of well in terms of production, that is characterized by damage or stimulation, whether the skin factor is either positive or negative. The capacity of reservoir in terms of transmissibility, because this PTA also serves as an input in reservoir simulation, where we discretize the entire reservoir into distinctive grids, and where there the transmissibility term plays a very important role. Also, we can find the current average reservoir pressure. That pressure is declining with time. So we do generally the SBHP survey, the static bottom hole pressure survey, once in 6 months to find out how our pressure is declining with time. Also, we can judge the reservoir limits. We can also find out well interference effects, such that if we have a pool, we have two wells here with a distinctive spacing. We can understand which well is affecting which well from interference test and pulse test. We can also find out well or reservoir specific parameters like the wellbore storage, the length of fracture and width of fracture and height of fracture, length of fault, from how much distance the fault is located from our well, or we can also find out the kV upon kh, the vertical to horizontal permeability ratio. So the main point is, why should we do well test? We can also find out some other mechanism or some other way to figure out our objectives. So we need to understand why should we do well test. So well test provides information that can be used for reliable planning of oil and gas field production and development, and reducing the financial risk in investment in oil and gas projects. So this reduction in risk of financial terms would be like if you have a field development plan approved by your respective government, the Ministry of Petroleum and Natural Gas, and we want to drill a new well in that field. But the previous well that we have drilled has shown that this field in the later time won't be more effective if we add a new well to that field. So that result would be figured out by the well test interpretation, because we can understand what is the reservoir limit and we can also understand what is the current reservoir pressure. So if we drill a new well, it is like we are increasing drawdown, in other words. So that could be a big risk to a company that is planning to invest more in that particular field. Also, the list of information that well test can provide would be the well test provides information not available in static model. So this static model is generally developed by the geologists when we try to convert a field from exploration to development. So this static model also needs inputs from the well test data. If we drill a new well in a particular field that is in exploratory stage, we can understand the reservoir parameters when we generally do EWT, also called as extended well tests. So these well tests will be running for 3 to 6 months to understand how our reservoir is performing. Because when you do the same test for more than 2 to 3 days, you might figure out the new reservoir boundaries. Because generally, to not lose production, we generally do the test for approx a day or 2 days, 24 to 48 hours. But if you leave the gauge for more than 3 to 4 days in the same well, in certain condition, you might estimate new reservoir boundaries depending on the radius of investigation of the pressure wave and the derivative that the pressure wave has told you. We can also increase reliability of geological interpretation and reserve estimates. This well test provides actual and potential productivity of the well tested. It collects reservoirs representative fluid sample for PVT and phase behavior analysis. This is a separate advanced topic where we also take fluid samples apart from well test data gathering, and also the flow assurance studies. This helps in identifying well problems such as sand production, asphalt or paraffin presence, water or gas burning. This is a typical design workflow, because when we try to run in the gauge, the first step is to run dummy gauge. So this dummy gauge will try to tell us what is the obstruction in the well bore. So this dummy gauge that is running before the primary or the EMG, we can understand is there any obstruction in the tubing. So we can clear that out and then we can run in the main gauge. So it will help us in identifying the well problems such as sand production, asphaltene or paraffin presence, water or gas burning. So when well test should be done? So well test can be done at any stage of reservoir life cycle. The purpose of carrying out well test at each stage may be different. The purpose is different, of course. If you want to monitor pressure, we will just go for SPG survey, the static bottom pressure, but we don't go for the complete build-up study. Similarly, if you want to understand what is your flowing bottom pressure at a current flow rate, you can also do that survey. That is completely fine. Some typical objective of well test at different stages of reservoir life cycle are: in exploration stage, we can understand the reservoir and fluid properties, also the reservoir deliverability. In appraisal or early stage of field development, we can refine our interpretation, their previous interpretation. Because what the EWT, the extended well test, is telling us, that can be refined in the new test, in the field development stage. Also in production stage, we can look at reservoir management. So we can understand need for well treatment, interference testing. One example that I can give you is that if your productivity index is too low, you can go for artificial lift installation. So this well test also can let the company or the investment strategy or whatever you call it, the company know that this well needs an AL installment and this well can't come on self flow or the natural reservoir flow. So that can be a good scenario of considering why we do well test during production stage for reservoir management. So types of well tests. There are two tests, two broad test wings, where we call one as transient tests and stabilized tests. So in transient tests, we have drawdown, build-up, multi-rate, interference, pulse, crystal test, and repeat formation test. In stabilized tests, we have reservoir limits test, also called as extended drawdown test, AOF test, the absolute open flow, where we consider our wellhead pressure to be at a zero, or the surface condition where we look at 14.7 psi. The gauge pressure is zero and atmospheric pressure is 14.7 psi. So we can also do AOF test to understand the ultimate reservoir deliverability. Also the hyper relationship establishment test. So to interpret transient tests, or to understand from what we can get from transient tests, so we do PTA, the pressure transient analysis. That is, you should define reservoir characteristics such as permeability, damage or stimulation, turbulence in the reservoir or in the wellbore, boundaries for reservoir shape, and also we can predict future rate or pressure decline trend. So these five broadly come under the transient tests. Also for stabilized tests, when we call stabilized test, when the well has reached a flow regime called PSS, the pseudo steady state. So that means that reservoir boundary is now well defined and there is no flow after that reservoir boundary. So stabilized test will tell us the reservoir limit. That is also called as extended drawdown test. So these tests are used to define long-term production performance that are flow at various pressures. That is also called as multi-bean or multi-choke test. And the reserve estimation, of course, because we are knowing the reservoir limit up to what point or what investigation radius the transient can be reached. And after that, beyond that point, there is no more presence of reservoir. Maybe there could be a discontinuity, an unconformity, or a fault, or a channel. So we will now focus mostly on single and multi-well tests. So there are some pictorial representations for you guys to understand what we actually do and what we actually monitor through plots. So in single and multi-well tests, to broadly consider single well test, we lower the sensor, that is the memory gauge, the pressure gauge, and the well is allowed to flow. So if you look at the Q versus T profile, the flow rate versus time profile, the production is constant, the rate is constant, and the pressure is declining continuously, and it stabilizes at a point. So we generally perform this test for more than 8 hours to look at the pressure stabilization, and then we shut in the well for further testing, maybe for build-up test. So as the flow rate is being, the well is flowing at a constant production rate, the pressure is dropping and it stabilizes at a point. So this PWF, the ultimate low PWF, would be used to calculate PI, the productivity index for a well. Also in build-up test, the well is closed, and because then the Q will be zero, the production rate is zero, the gauge will be inside. So if you can see, the Q will be now zero with time, and the pressure buildup starts, and it reaches stabilized point. That could be maybe after 24 to 48 hours. So this test is like, we shut in a well and we monitor at another well, an offset well. So this can be also part of single and multi-well test. So single well test is single drawdown and single build-up test. This multi-well test is the same. So we monitor the pressure response of this well at a well that is at an offset distance. Maybe this is an infill well, that is the part of field development plan. Sensor is lowered in the offset well, and the well is flowing, and this well is shut in. So pressure and flow rate are recorded at the offset well. So if you can see at the offset well, the Q is same because the well is flowing at a constant rate, but the pressure is dropping initially and then it is rising because this well is shut in after this point. So you can see an increase in pressure because there is an obstruction at this point for this well. So until this point, until when the well is flowing, the pressure is dropping, and after this point it is building up even though the well is flowing. That is something unique in multi-well test. Also, if you look at multi-bean test or the multi-choke test that I have told you, so you first have a well that is flowing and you have another well that is flowing. So both the wells are flowing. The pressure is recorded in the offset well. So you can see initially the Q is zero in the offset well because the well is initially shut in, but the pressure is dropping because this well is flowing. And then both the wells are flowing. So the Q will be a constant value because the offset well is flowing where the gauge is in, and the pressure is dropped even more because these two wells are being drawn down or are being produced from the same pool or the same reservoir. So you have more drop in PWF when both the wells are flowing. on the same field or the same pool or the same reservoir. So from a typical drawdown test, you get a graph like this. You get a plot like this when you try to plot PWF and T. So if you can see the pressure drop, the PWF is dropping in the early time region. This is called the ETR, where your wellbore effects dominate. And then you have a shift or the transition zone from ETR to MTR. And during the MTR region, you have a constant slope. So this is technically the PWF versus log T. This is logarithm of time. So in the MTR region, the middle time region, you can find the slope of this middle time region and find the reservoir parameters, that is perm and skin factor. Similarly, from build-up test, that is the inverse of drawdown test, you have ETR and then transition and then MTR. So from MTR, the same thing. If you plot PWF versus log time, you get a MTR region and you can find the slope of this line, and then you can find your reservoir parameters, the perm and skin factor. From injection test. So injection test is generally done to understand your pressure behavior or the well behavior when you're injecting fluid. So this well is under injection stage. When you're injecting fluid, you're continuously applying pressure to this well. So the pressure builds up continuously. If you can see here, the Q is 0 because the well is shut in. This is static reservoir pressure, it is constant, and suddenly you inject. So when injection is going on, you generally like mark it as a negative flow rate because it is now injecting. So Q will be negative and your P will be increasing. The pressure in the reservoir will be increasing. The same thing from injection well test, you have a semi-log plot for PW versus log time, injection time. So from the MTR region of the injection plot, you can monitor your permanent skin factor. From injection fall-off test. So injection fall-off test, you initially inject the well. So this negative flow rate is to show that the well is being under injection, and then you shut in the well. So when you shut in the well, the Q will be 0 and the pressure is suddenly fall off or it falls off. So that is something unique in injection fall-off test. So this injection fall-off test is generally done in gas reservoirs or tight reservoirs because we want to understand what is the fracture injectivity or the fracture integration test. We generally use defit analysis. So to frac the well, to understand what is your fracture pressure. So from the same injection fall-off test, you have the pressure versus log time plot, and from the MTR region, you can find your reservoir parameters. From interference test, your objective is to understand the interference of one well through another well. So initially, you have two wells at a certain distance. This is the primary well, this is the offset well. So you monitor the pressure in the offset well, sensor is lowered in the offset well. So the well that is under test flows, but the well that is under response is shut in to understand what is your interference between these two wells. So if you can see, the Q is 0 because the well is shut in, but the pressure is increasing because this well is shut in and this well is drawing fluid. So depending on the response of pressure, you can understand what is the interference between these both tests. If the pressure falls down, you can see that the reservoir is extended till this well. But if the pressure is building up, you can understand that there is a discontinuity between these two wells. That is something unique. To reconfine or recharacterize your reservoir, the geology of the entire reservoir. Also from pulse test, you have a passive well, you have an active well. So this well is flowing where your sensor is lowered in the offset well, and this well is flowing. Both the wells are flowing. So in the active well, this is the active well. You have Q, a constant value of Q, then shut in, flowing, shut in, flowing. So if you can see during the shut in period of the active well, in observation well, your pressure is increasing. Suddenly, when you flow the well in active well at a constant production rate, your pressure declines in the observation well. So that is something understandable that these both are in communication with each other. So pulse test is generally used or done to understand the communication between both the wells that are under consideration. So these all will be taught in this course. So a typical summary: during production in single rate test, your pressure declines. During injection, your pressure builds up, and during flow and shut in, your pressure builds up. Similarly, in multi-rate tests, you can see your improvement in flow rate, constant rate 1, constant rate 2, and constant rate 3. And also you can see your pressure drop 1, 2, 3, and 4. So can anyone in the audience tell me how do we improve the production rate? How do we increase the production rate? What is something that we do on a well to increase the production rate? Maybe someone can type in the chat box or someone can unmute and tell me. Anyone? Yes, that's right. We try to alter the choke size. That is also called as beam size. So we increase the choke size. That choke size generally comes in 1 upon 64 millimeter. So we choose 2 choke size, 4 choke size, 6 choke size, 8 choke size. The moment we increase choke size, your production rate improves or multiplies, and your pressure drop also multiplies. So that is something important to understand. So also, if you look at the third graph, you're decreasing the production rate. So this is multi like flow test, build up, drawdown test, build up, drawdown, build up, drawdown. So if you can see your response and pressure during drawdown, your pressure is declining, and in the build up, your pressure is inclining, and during again the second drawdown, pressure is declining to a value more than the initial decline or the flowing bottom pressure value, the stabilization pressure, and again it is improving or inclining with a shut-in, and then with a less production rate, your flow rate is even more declining. Your pressure is declining. So this is a typical multi-rate test response as a summary. So if you look at the flow regimes, that is very important for designing a well test or to understand the physics behind well test. So we'll generally have three conditions: the transient condition, semi-steady state condition, and steady state condition. So in the three conditions, we try to generally maintain constant rate, but in the difference between these three conditions, the pressure response, the pressure that actually is important to us. So in this unsteady state condition or transient state condition, the pressure is a function of both radius and time, and also the derivative, the pressure with time, the change of pressure with time is also a function of both radius and time. So in transient condition, your pressure wave that is actually being monitored by your gauge that is running is trying to find the boundary. It hasn't found the boundary. So these both pressure as well as the pressure change are both functions of time. In semi-steady condition, the pressure or the actual pressure transient is realizing the effect of boundary. It is starting to realize. So if you look at the pressure change with radius at a typical extent of the radius, that will be 0. That means if you look at the response, if your well is here, your investigation radius is here, it is increasing, the pressure response is increasing, it is constant. So between these 2 points, the pressure response is constant. So the change in pressure with radius, this is the radius, this is the pressure, the change is constant at a certain radius RE. So that typically means that your reservoir boundary is felt. And also if you look at the change in pressure with time, it is constant. The pressure change is constant for all radiuses. Similarly, in steady state condition, where your boundary has reached and it is realized, your pressure is constant at R is equal to RE. So at this point of time, your pressure will be constant. There is no change in pressure. Similarly, with time, the change will be 0 for all R and T beyond this point. For all radius and time, the change of pressure with time will be 0. So these three are something important and unique to be understandable before you start interpreting or discussing about well testing. So to this webinar, because it's an induction webinar, I am briefing only on transient flow condition. But in the main course, we'll be briefing about all the conditions. So if you look at this transient condition, this is your production rate that is being drawn from this well. So your wave, the pressure wave, the transient is still searching for the boundary. It hasn't reached. So the same thing, your change of pressure with time will be a function of radius and time, and the pressure will be equal to Pi at R equal to RE. But you don't know what is your RE, because the wave hasn't reached a boundary. So this is a typical wave progression, the typical radius of investigation. So pressure transient migrates outward from the well without encountering any boundaries. So this is defined as a fluid dynamic condition. In this system, the pressure and volume change over time. The pressure and the volume change over time because of changes in the system flow condition, in transient flow condition. So this we need to understand the transient flow equation because it's the basis for every well test and its interpretation. So in steady state, quantity of fluid entering and leaving the porous medium are same. That is true because there is no accumulation. So whatever enters will be leaving the system, the closed system that we consider, the control volume. In case of unsteady state or transient flow, the rates of fluid entering and leaving the rates of fluid entering and leaving the porous system or the porous medium may not be same. Hence, the fluid content changes with time. If there is a gas encroachment or if the well or the flow is such that your pressure is declining below bubble point pressure, there is some instability because the pressure drops as it continuously is being produced or at separated condition. So this gas might install a new term called accumulation term. So we need to understand the continuity equation, which is also called as the mental balance equation. Mass entering an element volume of reservoir during a time interval delta t minus mass leaving an elemental volume of reservoir during time interval delta t should be equal to the mass accumulation during the same time interval. So this is the governing equation, the main governing equation in transient flow condition. Also, the other two governing equations will be transport equation and compressibility equation. Because I'm telling you that in transient flow, your fluid is the main important part. So we need to understand the compressibility. This describes change in volume of fluid as a function of pressure. Because the compressibility factor plays a very important role when we derive the diffusivity equation. Also in transport equation, we describe the fluid flow rate entering or leaving the elemental volume. So we need to first understand what are initial and boundary condition. So the boundary condition will be the rate of production is constant because we are drawing this fluid at same production rate, and also across the boundary there is no flow. And reservoir behaves like infinite reservoir that we also call as IARF, infinite acting radial flow, with radius tending to infinity as R tends to infinity. The initial condition would be at time t is equal to 0. The pressure in the reservoir for all values of R are same. Before the start of this well test, the pressure in the reservoir is same. The pressure is same across the reservoir and the reservoir is homogeneous. So these assumptions that are made are well is vertical. The flow is horizontal across the reservoir. The reservoir is homogeneous. The perforation that we do are fully penetrated, and the fluid flow is single phase fluid. Maybe it is either oil or gas. So now we look at each equation. The first equation is continuity equation. That is the diffusivity equation or conservation of mass that we derive. That we'll derive in the actual course. 1 by r, dou by dou of r u p. R is the radius, u is the fluid velocity or the superficial velocity, and p is the pressure. Should be equal to dou by dou of phi into p, the porosity times pressure. This is a typical continuity equation that we will be deriving. The transport equation is typical Darcy equation only, where you put your u here. This u will be equal to k by mu dou p upon dou r. So can anyone just summarize about Darcy equation, maybe in chat if you're comfortable, or you can also unmute and tell what is Darcy equation, what does it signify, and why are we telling that Darcy equation is a transport equation? Anyone? Just in single line define Darcy equation. Okay. So Darcy equation relates your fluid flow rate that is given by fluid velocity to your pressure drop. So U will be proportional to delta P or the pressure gradient dou P upon dou R. So this K by mu will be the proportionality constants. K will be the permeability and mu is the viscosity. So this U can be written as Q by A. So if you look at Darcy units and as well as field units, so this Q in cc upon second, the centimeter cube upon second will be Ka by mu dp by dx. So K is in Darcy, A is in centimeter square, and mu is in centipoise. dp the pressure drop in atmosphere, and dx in centimeter, the pressure drop across the entire reservoir. Similarly, in field units, this Q in barrel upon day will be a constant that is changed or that is derived from your Darcy unit system times K in millidarcy, area in feet square, viscosity in centipoise, dp in psia, and dx in feet. So this is something that we need to understand to look at the transient flow equation. That is a basis of well test. So the concept of skin and its inclusion in flow equations. So if you look at this typical response of pressure, so in the near wellbore region, at a radius r equal to rs, the skin region. So you can see the pressure drop is constant till r is equal to rs, but below r is equal to rs, the pressure is either increasing or decreasing. So what does it mean? So there is more drop in pressure if your near wellbore region is damaged. So this drop is due to maybe sand presence or fines migration or whatever it could be, reservoir damage. So we look at damage permeability Ks, and if pressure is increasing, that means it is stimulated or improved. So we look at improved permeability Ks. And the bulk reservoir has an unaltered zone with permeability K. So positive skin, that could be due to wellbore damage by mud filtrate, invasion, cement slurry invasion, whatever it could be. Enter the formation during drilling, completion, or workover operation. So this damaged zone with altered permeability is called skin zone. In negative skin, when your actual response of pressure is increasing because there is an improved permeability. Well stimulation due to acid treatment or fracturing causes improvement in the formation permeability around the wellbore. So this additional pressure drop due to the decreased permeability is referred to as delta P skin. That is to be included in the actual transport equation or the transient flow equation. So if you look at the actual Q, that is a factor that is considering as delta P or dou P. So this delta P, again derived from Darcy law, in radial system would be P minus PWF, also Q mu by 2 pi C1, the constant KH, times ln RE by RW in radial system. So this delta P skin is now included because this delta P skin can either increase the pressure drop or decrease the pressure drop. So we generally consider that delta P skin as a negative term. So delta P in skin zone due to K skin minus delta P in skin zone due to K. So in skin zone due to K skin across the damage zone, and in skin zone due to actual K, that is delta P skin. So we generally derive it as a difference, and then we understand that delta P skin should be equal to the actual Q mu by 2 pi KH into constant times K by K skin minus 1 into ln R skin by RW. So this is a typical equation used to monitor or to understand what is your value of delta P skin, the additional pressure drop caused by delta P skin. It can be negative or positive. So now the transport equation, actual transport flow equation oil well test will be this. The pressure at a distinctive radius and time will be the initial pressure minus this entire term that is derived. 162.6 Q mu by KH times log KT by 5 mu R CT RW square or R square at a distinctive radius R minus 3.23 plus 0.87 S. So this actual pressure equation typically is the response to IARF, infinite acting radial flow. So we will include now the delta P skin term to this pressure drop, that is Pi minus PWF. Plus delta P skin will be adding, that is already added here, that is giving you 0.87 S additional term. So your pressure will be now a term more than this actual term by 0.87 times skin. If skin is positive, your pressure is more. If skin is negative, pressure is less. So for a plot of this bottom hole flowing pressure versus Pi. So if you observe here, when the moment you have converted your P to PWF, your R is now RW, the elbow radius, because you're monitoring your flowing bottom pressure at your elbow radius only. So PWF plot versus log T will give us a straight line in the MTR region that is now used to find the permeability. From the slope, you can find your permeability. The slope will be equal to this factor 162.6 Q mu by 2 by KH. So by rearranging M and K, you can find your permeability. Okay, so a typical summary or introduction to fluid steady state flow. This type of flow regime occurs in a closed reservoir when the transient has moved to all the physical boundaries of the reservoir. So if you observe, the transient now is stable beyond this distance from reservoir. So this is something called like stability has reached, and the pressure is now in equilibrium stage. The boundary has felt. That is understood from the log plot that we are going to discuss soon. The boundaries include surrounding producing wells also. This flow test analysis is only valid for drawdown tests or injection data while the well is flowing. In steady state flow, you can see beyond this point, the pressure is not constant. There is no change of pressure with time. Steady state flow describes the flow condition where the fluid properties, temperature, pressure, viscosity, and velocity at any location in the reservoir do not change with time beyond a point. That is important. Also, the mass flow rate is constant in a steady state flow system. This means that there is no accumulation of mass inside any component in the system. So in any component or across any control volume in the system, there is no accumulation. Whatever is entering is leaving. That is the basic significance of steady state flow. So summary, the pressure versus time response will be like this. In steady state flow, it is constant. In semi-steady state, it is declining constantly. The rate of change of pressure is constant at any point. In unsteady state flow, it is declining exponentially because it is function of both radius and time. I is position and T is time. So now we need to understand the RINV, the radius of investigation, because in any well test, we will monitor the radius of investigation to understand up to what point in the reservoir your pressure wave has reached. So this RI is now defined as from these all parameters. Based on the time T, this T up to what point in a given time your wave has reached, that will be given by 948 mu CT RI square by K. So don't worry, we'll be deriving everything in the course. So depending on the investigation radius or time is defined. So do you know the time now? Because you know that up to 20 hours your well test has been done. So by inputting this time, you can read the equation to understand your radius of investigation. So up to this feet, maybe your pressure wave has reached. If it is now stable, you can understand the boundary has felt, and this is my ultimate reservoir boundary. But if it is not stable, if it is still increasing, you can understand that you need to do well test for even more time. So this RINV is a typical diagnostic that will tell you up to what point in the reservoir your actual transient, the pressure transient has reached. Also the principle of superposition. So if you look at the principle of superposition, it identifies that the total pressure drop at any position in the reservoir area is the total of the pressure drop at the position affected by flow in each of the wells. If you do multi-rate tests, maybe if you do a multi-well testing, you have a single well and you have two observation wells. So in that scenario, you need this principle of superposition where the actual pressure drop is now a sum of the pressure drops in each of the well, delta P1, or this is a multi-beam test, maybe the pressure drop 1 plus pressure drop 2 plus pressure drop 3. So the entire drop will be now having these three components, delta P1, delta P2, and delta P3. Also, in terms of flow rate, the principle indicates the pressure disturbance will spread across the reservoir, and also the flow is now unique in each distinct systems. So the source of disturbance is now monitored by totaling the flow rate as well as pressure drop. So the entire QT will be now equal to Q1 plus Q2 plus Q3. So this Q3 is typically now Q3 minus Q2, the actual increase in pressure, increase in flow rate. And at Q2, you have Q2 minus Q1. So from Q1, the flow rate is now multiplied because you are dropping a pressure by delta P2. Your flow rate is now increasing from Q1 to Q2 with a factor Q2 minus Q1. Similarly, if you're dropping the pressure drop more by delta P3, your flow rate is now increasing from Q2 to Q3 with a factor Q3 minus Q2. So the total QT will be Q1 plus Q2 plus Q3. So this superposition principle is important in the long run for well test design. So now the interpretation workflow. So the first step will be to gather well test data. Second step will be analysis and quality control of data, because we need to remove some irregularities or noise. Then we do deconvolution. Don't get panicked. We will discuss every step clearly in the actual course. We also indicate flow regimes depending on the diagnostic plot. We select the reservoir model from the model parameters. We estimate model parameters by fine tuning. We can also simulate or history match pressure response, and we validate the result. So in early time, these are the typical near wellbore effects. well bore storage, skin, fractures, partial penetration effect, and horizontal well. In middle time, the reservoir behavior is found where we understand homogeneous or heterogeneous behavior of the reservoir by modeling, by selecting a reservoir model. And in late time, we have specified rate, specified pressure, and leaky boundary from boundary effects. So these all are added or looked in a coupling manner that will typically complete a well-test interpretation model. So we calculate the model behavior, we compare the data, and then we again check for the consistency. It is consistent, yes. Then we go for interpretation model. If there is another model required, yes. Then again we go back to the identification part and we do verification, compare the data. If it is no, then we end the interpretation and we give the results to our team. So this diagnostic plot, this is something important. So this is your typical pressure wave response. The transient pressure, log delta versus log t, log delta t. So you can see a pressure is increasing in the near wellbore region due to wellbore storage effect. It is again constant in the bulk reservoir, and suddenly it is increasing in radial infinite active region, and the boundary effect is felt because the pressure is now increasing. It means that there is a increase in pressure with time. That means your boundary has felt. There is some support of pressure. That could be no flow boundary, a closed system, or a constant pressure boundary. So if you look at the diagnostic plot, the log plot, the blue color line typically shows your actual pressure response, the transient, and the red color line, the derivative, shows your log plot or the derivative curve. So if you look at this up to your 1.5 log cycle, you can see from the well test I started 0.01 to 0.1, from 0.1 to somewhere around 0.5. This is a 1.5 log cycle time. Up to that point of time, you have your early time region or the early time effects dominating your well test data or your behavior of reservoir. Then you have middle time region where your reservoir wave, the pressure transient has reached a bulk of reservoir. That could be either homogeneous reservoir or heterogeneous reservoir. That is depending on your model that you set. From this middle time region, you can find your KH product, the permeability thickness product, or also called as transmissivity. If you divide this KH by H, the net pay, you'll get your permeability. That is typical interpretation workflow. And once you have crossed your middle time region, you can now observe that your response of pressure, it is now having a positive slope. That means your boundary of the reservoir has felt. Some sensitivity, if you look at this typical pressure derivative and pressure response, the pressure curve and pressure derivative curve, if your early time region is now towards left, that means your wellbore storage is now decreasing. If it is towards right, your wellbore storage coefficient is increasing. If your derivative across the transition region from early time to middle time region, if the derivative is below or there is more gap between your actual pressure response and derivative response, your either C or S increases. If it is going down, your C or S, the wellbore storage coefficient and skin factor decreases. And if you're in the middle time region, if your response of derivative is moving down, the separation is increasing, it means your K is increasing, and the separation is decreasing, it means your K is decreasing. Similarly, in the pressure curve or the delta P curve, if it is going towards top, that means the skin is increasing or K is decreasing. If it is going towards bottom, the skin is decreasing or K is increasing. That is something important and should be known prior to interpretation. So a typical slopes of the diagnostic plot will be, if it is linear, your slope of logarithmic derivative on log of plot is half. For bilinear flow, it is 1/4. For volumetric reservoir, it is 1. For radial flow, it is 0. And spherical flow, it is -half. So depending on the response of pressure, if you can observe here, what this 1 represents. If you look, if maybe we look at -half. If you look at -half, for a change for a block, if you look at the block here, this is a typical, I'll just draw here so you can understand. In this block, your change in pressure derivative or pressure, it is of one full block. But if you observe your x-axis, your change is now only half block. So only half of the block is now having this response. So that is -half slope. Similarly, in radial flow, if you observe this point, this part, your pressure is constant for the entire block and for the entire block. So that means the slope is 0. There is no change of slope. And for linear flow, similarly, For a full block of derivative or the pressure response, the delta P axis, there is half change in the x-axis, the time axis. That is half slope for linear flow. So some conclusions on this. The start and end of the flow time for every flow regime should then be determined using the log-log diagnostic plot. Currently, the log-log plot is the best accessible approach for characterizing infinite acting radial flow. Besides this, besides the log-log plot can also be used to characterize other flow systems such as linear flow, bilinear flow, spherical flow, fluid flow, and elbow storage. Some useful features of this log-log plot. That is the main essence of this PTA. So maybe you have already done some similar course in your course or your industry. But what differentiates this course from your previous courses we will be looking at detailed insights on recognized flow system using during well testing. We will discuss briefly on well test concepts. We will understand the design workflows. We will understand the interpretation workflows. We also will discuss on several reservoir models like dual porosity, radial composite, and dual permeability with practical examples in the field. So a simple example of this course will be this tool. Do anyone know about this tool? The primary pressure derivative? If you know, you can comment yes. The PPD. It is a very important tool, but many interpreters neglect this PPD. Okay, this PPD is called a primary pressure derivative that is used generally to understand your Welbor effect and its masking the reservoir effect. It is a new diagnostic tool in well test interpretation. So if you look at a typical response of a well somewhere in India, so this violet color plot shows your delta P curve, and your red color plot, sorry, the this line shows your delta P curve, and this red color line shows your derivative curve, and this violet color line shows your PPD, the primary pressure derivative. So if you observe at this point, you can see your PPD is declining up to this point, but after this point, it is having a different slope. It has increased. Again, it is declining. So this means that there is some effect of Welbor. So PPD was developed to identify Welbor effects within a pressure response so that they can be separated from reservoir effect. So this PPD will let us understand the effect of Welbor more than the reservoir effect. So it will try to help us understand this response of your derivative is not due to reservoir effect but due to Welbor effect. So that examples of that Welbor effect could be the redistribution of phase due to liquid influx. Maybe there is some leaking from reservoir to Welbor during shut-in period. There could be gauge malfunction. There may be some Welbor cleanup operation required, or there could be some seismic effect due to some overburden or underburden, whatever it is. So the d by d delta t of delta p is your derivative PPD, and your actual derivative is d of delta p by d of ln delta t. So this PPD will also be discussed in this course. This is an example. We will also discuss some more advancements in this course. That is something unique about this course. So I suggest you to take this course. Some data for you. History of well test analysis. Late 50s, we have straight lines and Laplace transforms to figure out the homogeneous reservoir behavior. In late 60s and early 70s, we have type curve analysis and using green functions to understand near Welbor effects. In late 70s, we have type curves with independent variables to model dual porosity reservoir. In mid 80s, we have derivatives, the pressure derivative that is established or found out in mid 80s to find heterogeneous reservoir behavior and boundaries. In late 90s, we have CAD, computed design and analysis, where we also have downhole rate measurements and integration with interpretation models from other data for multi-layered reservoirs. Because generally in every field, if you can see, there is no single reservoir that is used in production. We have multi-reservoirs, multi-zones. So in multi-layered reservoirs, we need data analysis of using computer and advanced equipment. So also this is another presentation of that same table. In 50s to 70s, we have straight lines. The identification is poor and verification is also poor. It is none. There is no verification, but because the industry has just evolved, in this entire global scenario. So we are unable to verify the results of this straighten approach. In 70s to 80s, we have type curve analysis. The identification of this type curve analysis by hand is fair, and also by computer is fair, and verification is fair by hand and by computer is good. In late 80s, we have derivative created by hand, it is good, and by computer is very good. Identification is very good. And also when we verify that derivative by hand, it is fair, and by computer it is very good verification. So that is the reason why we have several tools like Kappa Sapphire, the typical like the hit well test design tool in the entire world. Also, we have several other tools like interpret from paradigm. That is also a good tool for well test design and interpretation, and some more tools available. So in this course, to just understand what we will teach, the first week will be covered on the basic concepts of well test analysis, which include basic concepts, steady state, semi-steady state, and transient well performance, the radial flow theory, and diffusivity equation. In second week, we will look at the interpretation of well test data, the principle of superposition, the build-up and drawdown testing, similar canals, and the reservoir pressure estimation. In week 3, we continue the interpretation by modeling wellbore storage and type curve matching, the derivative and diagnostic analysis, the skin factor and formation damage, and also investigation radius. In week 4, we will look at the well test models for different systems like radial composite, well in a bounded drainage area, channel stands and parallel faults, and also we will look at the design approach. In week 5, we will cover special topics like horizontal well testing, hydraulically fractured wells, dual porosity, double permeability systems. So this is a typical plan of this course. We might also improve this plan depending on the requirement of you people. So depending on that, we are planning this course. So this course currently would be for 5 days, but it can be extended also depending on the requirement and the need. So this is the end of webinar. If you have any doubts, you can shoot. Any doubts on the course or the content that we have just discussed, you can just tell me. So initially we'll use Excel for better understanding or for initial understanding, and we are trying off for a software also, so that we can like look at the entire design and interpretation. If we are unable to get the software, we will be looking at some videos and screenshots that can be of good help, but we are trying on software. Any other questions? No, you are supposed to take the course. You can't join on all the other days. This webinar is to let you know about this course. Do I have to pay? This will be answered by the Advantage learning platform. Please contact them. Any
Okay,
more
sir. Here
doubts?
we
Yeah.
conclude the session now.
Okay.
Guys, anybody have any query, please ask on the group regarding the training program and all.
Please,
Sir,
I have
that's
a
all from my
question.
side. Yes, this is clear.
Please, I'm a well testing operator. Is there any opportunity in India to work?
In India to work, this is a unique question that at this point of time I won't be able to answer, but we can figure out. We can look at prospects Maybe once you take the course, we will discuss. It depends on your
Okay,
qualification
so
and your experience. Yes, you can
yeah,
discuss.
I have offshore experience.
Okay. So thank you for your presence in this webinar. Uh, whatever questions you are having, you can ask in the group so that the team will be able to answer. I hope all of you will be attending this course. Thank
Thank you,
you.
sir. Thank you, sir. Thank you all.